Hey guys, this video is for identifying unknown metals using calorimetry. By the way, you do not need to adjust your phone. I am blonde now. That happened in the past week. It happens to the best of us at some point in time, all right? All right, so I have the lab in front of me. Obviously, if you've skimmed through the lab, we're gonna have to make some modifications, but I am gonna run the lab to the best of my ability. So this lab is really about calorimetry, which is really just about measuring how energy transfers from one location to another. And so being able to determine how much energy is in an object based on how much energy it passes on to its surroundings. So what we're gonna start with is a block, which I don't have a metal block. I mean, not many people do at their homes. So I am using a series of teaspoons. I'm using a measuring spoon set because it's all I had that was metal and small enough to fit in my fake calorimeter. So what we want to do is basically say, okay, we know the temperature of this, we know the temperature of this, and so we want to see how much energy the teaspoons actually transfer into the water, and then we'll deal with the calculations after that, okay? So what I have done to start is I have set up my quote-unquote calorimeter, aka my, hold on, need y'all to hush. Okay. My Thunder Ridge coffee cup. And in here I've put in 200 milliliters of water. So that is gonna be our first piece of information. And something we've talked about earlier in the year, but it's very likely it's been forgotten on us, is that 1 milliliter of water is about 1 gram of water. So 200 milliliters of water is about 200 grams of water. So that's the mass of the water we're gonna be dealing with. We are doing a delta H calculation, so we will need mass, we will need delta T, and we will need specific heat capacity to determine the delta H of the water. So the mass of the water, these loud measuring spoons over there. The mass of the water, as mentioned, is 200. To get the initial temperature of this water, I have my LabQuest here. Ooh. And I've plugged in my temperature probe. I'm gonna put it in the water, give it a minute to kind of settle out, okay? So while I'm doing that, I'm gonna discuss kind of what we're gonna do here. So right now I have the measuring spoons boiling in water. Now why am I doing that? Well, because I need them to be at a higher temperature, and if I just took like a blowtorch to them to try to heat them up, I wouldn't be able to determine what their temperature is. But because metals absorb heat so easily, I'm going to be able to take the temperature of the water in the pan on the stove and use that to determine what the temperature of the metal actually is. So right now it looks like our temperature in our calorimeter, so that will be T H2O initial is 22.2. Well, that's easy. 22.2 degrees Celsius. So the temperature of the water in its initial state is 22.2 degrees Celsius. There's a crazy cat running around this apartment, so if at some point in time you notice that, I apologize, right? Okay, so let's figure out the temperature of the water in the boiling pan. Hey! She's already up to her antics. Just 1 second. Okay, looks like it's 93.3. So that is the temperature of the metal initial, okay? So even though I put it in water on the stove, that's the temperature of the metal initial because that's the temperature that we are assuming the metal is at in its initial state, and that was 93.3? I forgot. 93.3. We're going to go with 93.3, okay? So as a reminder, you guys may remember we talked about in our in previous units, and it's just kind of a life skill to know, that water boils below 100 degrees in Colorado because we have less atmospheric pressure. So with less atmospheric pressure, it means the water can boil more easily. So what we are going to do is transfer the measuring spoons into the calorimeter where we know the temperature inside there is 22.2. Just shaking this to try to get it back to room temperature so that we're not seeing a weird temperature change. I wish I had 2 temperature probes, which is what we would usually do in the classroom, but I only grabbed 1 in my mad dash out of the classroom. All right, so put this in here. Swirl that around, see if I can get it to balance down a little bit. We're getting there, we're getting there. We want to get it back as close as possible to 22.2, okay? Yeah, again, if you hear some weird sounds, my roommate's cat is darting through a little tube and having the time of her life, as one would if they were a cat. Okay, so our temperature is still dropping. I want to make sure I get it back down to 22.2. I don't want to have any issues there. There she goes. Here, 22.2. How y'all doing? Anyone know why I'm dipping it in the water and then shaking it in the air? Think about that. Phase changes. Okay, so it is at 22.2. Perfect. All right, so I'm going to put that inside there. I'm going to go ahead and keep it in the lid, but take the lid off because I'm going to need to be maneuvering. And so what I'm going to do is transfer the measuring spoons into here as quickly as possible, get the lid on, and try to get that final temperature. Okay, so let's see how I do. I'm swirling it around a little bit just to make sure the water fully coats the metal. Oh yeah, we get some temperature change in here. Yeah. All right. Looks like the highest temperature it's getting to 27.4. 27.4. All right. So 27.4 is two different temperatures. So pay attention. It is the temperature of the water final, and then our assumption can also be that if the metal measuring spoons transfer all of their energy out, that is also temperature 27.4. Had to write it down really quick before I forgot it. Temperature of the metal final. Okay, so the water and the metal change temperature at different rates because they're made out of different things. If you remember the virtual lab, we know that water and metals increase and decrease temperature at different rates. So we can expect that she's going crazy. We can expect that the metal is going to heat and cool faster than the water is. Okay, so what we can now start doing is I'm going to push my calorimeter to the side. Obviously, hopefully we know that if this were to be a better scientific experiment, we would run more than one trial so we can take the average, etc., and get it from there. Okay. So what we are going to do is we need to figure out how much energy was lost by the metal. But I wasn't taking the temperature inside the metal. So it's difficult for me to do that unless I first calculate how much energy is gained by the water. So the idea there being that whatever was in the metal transferred into the water. So if I can't measure what left the metal, I should be able to measure what entered the water. So I'm going to start, and I'm going to help you guys with the first part of the calculations. So let me get it written down. I hope I wrote down all of the pieces of information that I needed. Okay, so this is the equation I'm going to use initially. I'm going to start by determining what is the delta H of the water, how much energy actually came out of the water. Because our final goal here, let me go ahead and give you that. Delta H of the metal, mass of the metal, delta T of the metal, CP of the metal. So what we have is the mass of the metal, which you don't have, but I have, and I will tell you in a minute. The mass of the metal, we have the change in temperature of the metal, and we are going to be able to figure out the delta H of the metal because our final goal is to try to figure out what is the specific heat capacity of the metal, and therefore what is the metal actually made of, or what are my teaspoons actually made of, okay? So the first step is going to be we want to figure out what happened to the water. So delta H of the water is equal to the mass of the water, which we said was 200 grams, times the delta T of the water. Remember, that's always final minus initial. So the final temperature was 27.4 minus the initial temperature, which is 22.2. And then the specific heat capacity for liquid water is 4.18 joules per gram degree Celsius. Okay? So this is where I'm at right now with my calculation. So I'm determining the delta H of the water with 200 grams of water with that temperature change and that substance. Okay? So let's see. Perfect. Luna. All right. Don't worry. I'll make sure you guys get a chance to see this crazy cat at some point. So 200 times 27.4 minus 22.2 should be what? 5.2? Yeah. Times 5.2 times 4.18. So it says, okay, hold on. Let me just make sure that's right, because that seems like a lot of joules of energy. So, okay, 27.4 minus 22.2. Yep, 5.2 times 200 times 4.18. It is what it is. So the delta H of the water I have as 4347.2 joules of energy. So I'm not going to round that to sig figs or anything yet because it's not a final answer. So I got 4347.2 joules of energy. Okay. Now that's what the water gained. So if something gains energy, it goes up in energy, so that's positive. If something loses energy, it goes down in energy, so that's negative. So if the water gained 4347.2 joules, that means that the metal lost 4347.2 joules, which mathematically would be written as a negative. So the big thing there in calorimetry is just realizing that if a certain thing gains energy and another thing lost it, they just do the opposite of each other, basically. So in this case, we have that. Now, we can plug that in for our delta H of our metal, 4347.2 joules. The mass of the metal was 24.0 grams. The delta T of the metal, we said the final temperature was 27.4 degrees Celsius. Ooh, I messed up. Minus the initial temperature, which was 93.3 degrees Celsius. And we are solving for specific heat of the metal, okay? So what I want you to do with this assignment, the way that you are going to submit this assignment for a grade is I would like to see your calculations, which we just did, but work them out or put them onto your digital copy or whatever you're going to do. It's okay if you want to do it on paper and just submit a picture. Second thing I want you to do is do what it does say under data. I would like to see you put together a data table with all the information we just took down, make it into a neat, organized fashion. And then the final task is that post-lab analysis part D. I would like for you to go online and come up with a logical, correct answer to what these teaspoons are made out of, okay? Now, obviously, if you get back like sodium, well, I didn't die, which means it's not sodium because sodium would have exploded in the water. So it's gonna have to be a logical metal, something that would be normal. So we're gonna try our best. Obviously, I do not have a high quality calorimeter. We did not do 3 trials. So if the value comes out to be something absurd and it says, oh, it must be made out of oxygen, well, try your best. And then just put down, this is what I found. Obviously, I don't necessarily believe that's a fact. If you want to include any research that you determine to figure out what it probably is, that might be something good as well. If you do happen to get a direct relationship, awesome. But don't cheat it. Obviously, I'm not looking for you to, I'm looking to see that you ran your calculations correctly. I'm looking to see that you are able to run research and determine, okay, what substance is likely the substance that matches this specific heat capacity. But don't just fake it and say, oh my gosh, my calculations came out perfectly to this answer when they actually didn't, okay? I'm not gonna be counting off or anything like that. I'm counting off for, did you do it? And did you actually run the calculation correctly? Not whether or not you truly believe that the measuring spoons are made out of carbon or something like that. All right, 1 second. As promised, say hi, Luna. Say hi. Hey. This is my roommate's cat, and she is quite the kitten. Hi. Hi. You want to get down? All right. All right. Thank you, guys, and I will hope to see your lab soon.